So hi everyone. Thank you for being here today. So today we'll have Sophie Langer from TU Darmstadt, who will talk about deep learning with statistics, improving neural networks with statistical theory. So please go ahead.
Thank you. Thank you for the introduction, and hi everybody. So yeah, my name is Sophie Langer and I'm from the Technical University in Darmstadt, and today I'm going to talk about deep learning meets statistics, improving neural networks with statistical theory. And I would like to start with a short motivation of the topic. Some of you might heard about the successful results of deep learning in various applications, like in the speech and pattern recognition, in the field of autonomous driving, or also in the medical field. And the problem behind these successful results is that we do not really understand why. So we have some sort of a lack of mathematical understanding. We just have successful applications but cannot explain it from a theoretical point of view. And the aim of many researchers right now is to also gain a better theoretical understanding of deep learning, and to understand the properties of these networks. And that's also part of my research, or what I did in my PhD thesis and also in my time afterwards as a postdoc. So I have considered a deep neural network from a statistical perspective, which means that I have analyzed deep neural networks in the sense of nonparametric regression. In particular, I have considered least squares regression estimates, which are using deep neural networks. The problem why we have this lag between the theory and practice is actually that describing a procedure of deep neural networks at hand is a highly complex task. So first of all, we have to think about the right number of hidden layers. We have to think about the number of neurons per layer. Then we have to choose the right activation function. And finally, one has to describe the optimization algorithm, which is used to optimize the weights in the networks. And that's why one can divide the theoretical results which we have right now. So there are some interesting results, but they are like roughly divided in three parts. We have results considering the expressivity, which means that they look which kind of functions can be expressed by neural networks. Then we have some generalization results, trying to answer questions about why do these networks generalize well on unknown new data. And here's also all the statistical theory behind it. And then we have some optimization results, which are considering the optimization algorithm of this network, of these networks, like the gradient descent or maybe stochastic gradient descent. And they're like analyzing the energy landscape. The problem of these unilateral results is that they do not take into account all of the three aspects together. So we only have the results here in these circles, but not in the intersections. And this in turn means we get a better understanding of some parts of the network, so some parameters, but we cannot use the results to improve estimators in practice, as we are not able to implement the estimator in a simulation study or also in a practical application. And the question I was dealing with, and also some of my colleagues, is should it not be the aim of statistical theory to not only understand but also improve estimators in practice? And for me, the answer is yes, and also for my colleagues. And that's why we really tried to analyze all three aspects of deep learning together. And this is what we could show until today. And this result, which I will present you today in a more detailed way, is based on a joint work with Michael Kohler and Alina Braun from the Technical University in Darmstadt and Harro Walk from the University in Stuttgart. And what we did is that we analyzed shallow neural networks, which were learned by gradient descent. And for these networks, so these are really the simplest form of networks, so the one hidden layer networks, we could show good rate of convergence results for these networks, and we could show improved performance on simulated data. And that's why we decided for the title, The Smoking Gun, of this article. So we consider this finding as a smoking gun of deep learning theory, as it shows for the first time that statistical theory can not only be used to understand some parts, but also to improve estimators in practice. And that's where we want to go, right? So we want to really use the statistical theory for improved estimators in practice. Okay, but I want to show you what we did in detail. And therefore, I want to give you a quick introduction in non-parametric regression first. So what we want to do is that we want to study the statistical performance of neural networks. And the most convenient way to do this is to analyze neural networks in the context of non-parametric regression. But what is non-parametric regression? What we have given is a prediction problem. We have given an RD times R-valued random vector x, y, and our aim is to find a functional relation between x and y. So we are searching for a function f star with the input of x, which predicts y well. Okay? And how do we want to find this, or what should hold for this function? So we are searching for a function f star such that the L2 risk, which is defined in this way here, is minimal. And now one can really compute this minimum, and one can show that this minimum holds for m of x, and m of x is the expectation of y conditioned to x equal to x. And this is why one calls m the so-called regression function. So now we would be finished when we would know the distribution of x and y. Unfortunately, this is not the case in practical applications. So the distribution of x and y is unknown. The only thing we have given is a set of n IID observations, x1, y1 to xn, yn, which have the same distribution as x and y. And the aim is now to reconstruct our regression function m by an estimator mn, which uses these informations dn. And our aim is to construct the estimator in a way that this L2 error here is small. And that's what we want to do with neural networks. So now we are considering estimators which are based on a function class of neural networks. And therefore, I want to show you a result of Andrew Barron, and this one goes back to the 1990s. And his result also analyzed shallow neural networks. And here I have written a shallow neural network. So what is happening here? First of all, in the shallow neural network, we compute the weighted sum of the inputs. Then we shift this weighted sum by a so-called bias term, apply an activation function, and finally compute the weighted sum of all these so-called neurons. Okay. And in this result, the number of neurons is root n. And here we have these outer weights alpha k, and we have a further restriction on these outer weights. The L1 norm of these weights is restricted by Ln. Okay, and alpha, beta, and gamma. Beta is a d-dimensional real vector, and alpha and gamma are real values. Furthermore, the activation function is chosen to be a so-called sigmoidal activation function, which has the property that it's some sort of an S shape, and for u to infinity, this function converges to 1, and for u to minus infinity, this function converges to 0. Okay, and so what he did is that he used this function space Fn to compute an estimator mn. And how did he do this? He just considered or used the principle of least squares. So he chose the function f out of the function space Fn, which minimizes the L2 the least squares loss. Sorry. Okay, and what he could show for this estimator is that when he considers the expected L2 error, then he can bound this error by constant times log n to the 5 times 1 over root n in case that m, so here this function, regression function here, in case that the Fourier transform of the regression function has a finite first moment. Okay, and that was kind of an interesting result, as here the convergence rate, which is this last term here, does not depend on the input dimension of x. So we are able to circumvent this well-known curse of dimensionality as we get a convergence rate without the d in it. And This result is the one where our findings are based on. So what we did is that we studied now the rate of convergence of neural network estimators, which are learned by gradient descent. So maybe let's go back here. What Andrew Barron assumed is that this minimum here indeed exists. So he did not analyze the optimization of the network, so the gradient descent. And this is what we did now. So we really considered all the aspects and also trained our network by this gradient descent routine. And this is the notation we used. So first of all, we also considered the sigmoidal activation function, the same as Andrew Barron. And then we defined the shallow neural network in a similar form. So again, we have this weighted sum of the input here, shift this value by some gamma, and apply our activation function, and then compute the weighted sum. And we have here kn neurons, and these neurons depend on the sample size. And then we have here this weight vector w, and this weight vector depends on all the weights alpha, beta, and gamma. And this is the loss function we used. So again, we used the principle of least squares, and we extended this loss function. So we considered a panelized loss function. We extended this by some penalty term, which depends on the outer weights alpha. Okay. And this is how we initialized our weights. So first of all, we defined W0 to be the initial weights, and all the alphas in the beginning are chosen to be 0. And the inner weights beta and gamma are now independently randomly chosen. The beta are uniformly distributed on some sphere with some radius b, and the gamma are uniformly distributed on an interval minus b and root d to b and root d. And then we applied the gradient descent routine, and this is how this procedure works. So we update our weights in each step by considering the weights of the previous step and subtracting the learning rate times the gradient of our loss function on the value of the weights of the previous step. And this is what we do Tn times. So we have in total Tn gradient descent steps. So our final estimator is the network I've introduced to you after the updates of the weights with Tn steps, okay? And what we need to do to analyze this estimator theoretically is that we need to truncate this estimator on some level. So this level is constant times log n. And what does this mean? Mn is equal to mn tilde as long as its absolute value is smaller or equal to constant times log n. And otherwise, we just cut this value on this level, okay? And here is now the main assumption on our regression function, which we need to show our results. So what we assumed is for the Fourier transform of the regression function, which has this form here, that the absolute value is bounded by constant over the norm of omega to the d plus 1 plus epsilon, and epsilon is chosen out of the interval 0 to 1. So this assumption is a slightly sharper assumption compared to the result of Andrew Barron, but it's similar, okay? And this is what we could show. So under the assumption of our Fourier transform and with the number of neurons of order root n, a size of Bn of order n to the 5/2, a learning rate of order n to the minus 1.25, sorry, and a number of gradient descent steps of order 1 to the n to the 1.75, we can bound the expected L2 error of our estimate by constant times log n to the 4 times 1 over root n. So you see, we get the same rate of convergence as in the result of Andrew Barron, but this time our estimator is really learned by the gradient descent, and we are able to implement this estimator in a simulation. So here I just summarized on one slide what is the main trick of our proof. First of all, we set kn tilde to be kn over log n to the 4. And what we can show is that with high probability, we find sub-indices I1 to ikn tilde such that the corresponding inner weights, beta and gamma, can be chosen, and that we can adapt our outer weights in a way that the whole L2 error here is small. Okay? And then we perform our gradient descent routine, and we can show that these inner weights, which we chose randomly in the beginning, change only slightly. And this is because of the sigmoidal activation function. And then we just have to analyze the gradient descent and show that this is sufficiently to show our result, okay? Okay, and what we can further show is that this rate can only be slightly improved. So it's near to a minimax optimal convergence rate. This is shown in this result here. So we assume, again, the same thing as in our theorem before, and then we consider the minimax L2 error, expected L2 error here, and this error is larger or equal to constant times n over -1/2 minus 1 over d plus 1. And this infimum here is taken over with respect to all of the estimates mn had, which means that we consider all measurable functions of the data. So what we see is that in case that we choose d large, and this is really the case in many machine learning applications, then this rate gets close to our rate 1 over root n, right? So we have only here this factor 1 over d plus 1, which is the difference to our convergence rate. So we are close to the best possible rate in this setting. Okay, but I want to show you one more thing, and therefore we have to go back to the proof. So what we have seen is that this result mainly holds because of the random initialization of the inner weights and the good adjustment of the outer weights, right? So what we thought is we could maybe just fix the inner weights and just adjust the outer weights by the gradient descent routine. But this in turn would result in a simple linear least squares estimator, which can also easily be solved by a linear equation system. And that's what we did in the next step. So we used our statistical analysis to simplify our estimator. And this time, again, we chose the beta and gamma IID. The beta are, again, uniformly distributed on the sphere with some radius bn, and the gamma are uniformly distributed on this interval minus bn root d to bn root d. And then we define a corresponding linear function space. It's actually the same as the shallow neural network, but this time we choose just the beta and gamma randomly and only adjust these outer weights here. And then we define the corresponding estimator again by the principle of least squares. So we choose the function out of the function space Fn, which minimizes the least squares loss here. And again, we have to truncate this estimator on some level constant times log n. So again, the same thing when mn is smaller. When mn is smaller or equal to constant times log n, it's equal to mn tilde, and otherwise we just cut it on this level constant times log n. And this is the main result, which we could also show. So first of all, we had the same assumption on our Fourier transform. We set the number of summons in the linear estimator of order root n, and bn is chosen of this size here. And then we can bound the expected L2 error by constant times log n to the 4 times 1 over root n. So you see, we get the same convergence result as for our neural network learned by gradient descent. But this estimator is much faster in computation, as it can be easily solved by a linear equation system. So this is a real improvement compared to the network learned by gradient descent. And we had a further, in my opinion, interesting findings. So some of you might heard about the term representation learning, which was introduced by Goodfellow and co-authors in their book Deep Learning. And they describe representation learning as the ability of machine learning applications to learn a good inner hierarchical representation of the data. And it is considered as one of the key factors of deep learning. But when we now go in our result and consider the inner representation, we see that this inner representation are actually our sigma. And these sigma, again, depend on a randomly chosen beta and gamma. So in our case, it's not a representation learning. We would say it's much more a representation guessing. Okay, and that's a different thing compared to the term representation learning. Okay, and in the last step, I want to show you how we did the simulation for this estimator. So first of all, the setting. What we did is that we generated 200 or 400 independent observations, and we generated our y by mi of x plus sigma j times gamma I times epsilon. And the x here is uniformly distributed on this interval 0 to 1 to the d. The mi are different test functions, which I will introduce later. And then we have here epsilon, which is standard normally distributed. This sigma here denotes the noise of our observations, and it's chosen to be 0.05 or 0.2. And the gamma I is chosen in a way that it covers the range of the mi on x. And we compute this empirically by considering the interquartile range of 10 to the 5 different generations of mi of x. Okay. And this is how we implemented our estimator. So first of all, we chose our beta and gamma as in our theoretical result. So beta is chosen to be uniformly distributed on the sphere with some radius bn, and gamma is uniformly distributed on the interval minus bn root d to bn root d. And then we solve the outer weight, so the alpha, by solving a linear equation system. So that is actually our estimator. And the remaining parameters to choose are the bn and kn, and these two parameters are chosen by the splitting of the sample procedure, which means that we split our sample in two parts. We have a training sample of size 0.8 times n and the remaining test sample of size 0.2 times n. And what we do is that we choose bn and kn out of the sets here. And then we compute for each of the settings of bn and kn our estimator, or we train the estimator by the training set, and then evaluate the estimator with the test set. And finally, we choose the setting with the smallest empirical L2 error on the test sample. And this is how we finally choose our bn and kn. And here are our competitive approaches, and that are in fact some standard networks of Python's deep learning frameworks, TensorFlow and Keras. And here we have considered, on the one hand, the ReLU activation function, which is really famous in practice right now, and the sigmoidal activation function, so similar to our result. And we have considered networks with 1, 3, or 6 hidden layers. And finally, we have chosen the neurons by the splitting of the sample procedure, as I told you before. So again, we consider a training sample, train the estimator with all of these neurons, and then take the neuron with the smallest empirical error on the test sample. Okay. And here are our test functions, which we have considered. So the first test function is the exponential function with some sort of an additive input. The second function is a mixture between an additive model and a multiplicative model. The third function is some sort of a polynomial. The fourth function is a little bit different, as we have here in the first term the norm of x in it. And here are the two more functions, 5 and 6, and these are a little bit more complex. So the fifth function is a tangent hyperbolicus with a linear combination of the input. And the sixth function has some sort of an hierarchical structure. So we have two terms. the cotangents and the exponential function. And in this cotangents, for example, we have the exponential function, and in this exponential function we have the sinus. So we have really like a hierarchical structure of the function. And this is how we evaluated our results. So the quality of each of the estimators is now determined by the empirical L2 error, which has this form here. The M and I are our different estimators. The MI are our different test functions, and we consider these xn plus 1 to xn plus n, and these are newly generated independent realizations of our random value x. And this is how we evaluate the whole thing. At n is chosen to be 10 to the 5. And what we do is that we also normalize this value epsilon by as it depends. Also, the performance also depends on the test function, and that's why we decided to normalize the error by the error of the simplest estimate, which is the average of the observed data. Okay, that means that the errors on the next slides are these normalized errors. And as the x and epsilon are chosen randomly, we perform each estimation 50 times with different values of x and epsilon. And in the next slides, you will see the median and the interquartile range and brackets of these results. And here are our results. So we go through it for each test function. First of all, our function M1. And here is the LSQS, this is our estimator. So this is the abbreviation. And we see that our estimator outperforms the rest, the other approaches in all of the 4 settings. And in this case, the error of our estimator is at least 10 times smaller than the second best approach. So we have a real outperformance here. A similar result holds for the second approach. Again, our least squares estimator is the best approach with a 3 times better error compared to the second best approach, which is this ReLU network with 6 hidden layers. And also for the third function, we see that our least squares estimator is the best estimator. This time it's like 2 times better, but still a clear outperformance. Okay, in the fourth function, the thing is a little bit different. So this time, the least squares estimator is the best estimator for the smaller sample n equals to 200. But when we look at the higher sample, we see that the sigmoidal net with 3 hidden layers is 2 times better than our approach. So, and here it's even more, it's 4 times. Okay. For the fifth function, we see that our least squares estimator is only 1 times the best estimator, and in the other settings, it's slightly worse. So it's not a clear difference, but the sigmoidal net with 3 hidden layers is always better than our approach, except of this case here, n equal to 400 with noise 5%. Okay, and in the for the 6 functions, we have a clear outperformance of the ReLU networks. So this time the ReLU networks are at least 3 times, and for the higher sample, even more better than our least squares estimator. So you see, we have results. We have some pretty good results, but they're not completely convincing to us. So with the goal in mind to get an estimator which has an improved performance in practice, we have constructed a combined estimator which we abbreviated by this comp new. And what does the estimator do? It chooses between the estimator's new least squares and the standard nets, the one with the smallest empirical L2 error on the test data. Okay. And this estimator is now compared to a classical combined estimator, which we abbreviate by comp classic or comp class. And this estimator chooses of all of the standard nets, the one with the smallest empirical L2 error on the test sample. Okay, and I want also to show you this results. So first of all, for the first function, we have the same results for our new combined estimator as for our least squares estimator. So we see we outperform all other estimators in all of the 4 settings. The same holds for the second approach. So again, the new combined estimator is of the same size as our least squares estimator. In the third case, it's again the same. Here it's slightly worse, but it's only a little bit. And now here come the interesting cases. So in this case, the new combined estimator is in all of the 4 settings the best estimator. Sometimes the classical estimator is also good, but yeah, it's always the best or one of the best estimators, our new combined estimator. A similar result hold for the 5th function. So for the lower noise, our combined estimator is the best. And when we look at the higher noise, we see that our estimator is slightly worse compared to the combined classic, but it's only slightly, and it's less than 10%. So for us, it's not considered to be significant. And for the 6th activation, test function, sorry, I'm always saying activation function, we see that our new combined estimator is 2 for the higher sample together with the combined classic, the best estimator, and for the lower sample, our estimator is slightly worse, but again only a little bit, so it's not considered to be significant. So let me summarize what we have learned today. In a first step, we have analyzed an estimator, or neural network, which was learned by gradient descent. And this estimator really considered all 3 aspects of deep learning, namely the approximation, the generalization, and the optimization. So we are really in this intersection of all of these 3 research areas of deep learning. Furthermore, we could use our statistical insights to construct a simplified estimator, and this estimator is much faster in computation. And what we then could do is we implemented this estimator in a simulation study and could then compute a combined estimator, and this estimator outperforms all others in our simulation study. Okay, and I would like to end up with the following result, which I really which I really like. By far, the greatest danger for artificial intelligence is that people conclude too early that they understand it. I thank you for your attention.